Picture this. You're standing in your backyard on a clear night, gazing up at the stars scattered across the cosmic canvas above you. Each pinprick of light carries with it a story written in photons that have traveled unimaginable distances just to reach your eyes. But here's something that might make you pause mid-wonder. What if I told you that the universe you're looking at might actually be older than time itself? It sounds like a paradox wrapped in a riddle, doesn't it? How can anything be older than time? After all, we measure age using time. We say the universe is 13.8 billion years old, but what does that even mean if time itself has boundaries, beginnings, and perhaps even endings we haven't discovered yet? Tonight, we're going to embark on a journey that will challenge everything you think you know about time, space, and the very fabric of reality itself. Imagine for a moment that you could step outside of time, like stepping out of a moving train to watch it pass by. From this impossible vantage point, you might see something extraordinary, a universe that exists in a state beyond our conventional understanding of temporal flow, where the very concept of before and after becomes as meaningless as asking what's north of the North Pole. This isn't science fiction, though it might sound like it. This is cutting-edge cosmology, colliding with the deepest philosophical questions humanity has ever dared to ask. And the more we probe the edges of our cosmic understanding, the more we discover that reality might be far stranger and more beautiful than we ever imagined. The story begins, as many great scientific adventures do, with a simple observation that refused to make sense. In the early 20th century, astronomers were content with their picture of a static, eternal universe. It was a comfortable notion, the cosmos as an unchanging backdrop against which the small dramas of stellar birth and death played out. But then came Edwin Hubble, whose observations through the Mount Wilson Observatory's 100-inch telescope shattered this cosmic complacency forever. Hubble noticed something peculiar about distant galaxies. They were all moving away from us. Not only that, but the farther away they were, the faster they appeared to be receding. It was as if the entire universe was expanding like a balloon being inflated, with every point on the surface moving away from every other point. This discovery implied something revolutionary. If the universe was expanding now, then in the past it must have been smaller, denser, more compressed. Run this expansion backward in your mind, like rewinding a cosmic movie, and you arrive at a startling conclusion. There was a moment when everything, all matter, all energy, all of space itself, was concentrated in a single point of infinite density. Scientists called this moment the Big Bang, though it wasn't really a bang at all, and it didn't happen at any particular place. It was the beginning of space and time themselves. But here's where our story takes its first mind-bending turn. If time itself began with the Big Bang, what does it mean to ask what came before? It's not just that we don't know. The question might not even make sense. Asking what happened before time began is like asking what's 1 mile north of the North Pole. The very framework we use to understand before and after breaks down at this cosmic boundary. Yet this is exactly where modern cosmology gets fascinating, because while the Big Bang Theory explains how our universe evolved from a hot, dense state to the cool, sparse cosmos we see today, it doesn't actually explain the Big Bang itself. It's as if we have a detailed movie of everything that happened after the opening credits, but the opening credits themselves remain tantalizingly out of reach. Enter Alan Guth, a young physicist working in the late 1970s who was troubled by some nagging problems with the standard Big Bang model. Why, for instance, was the universe so remarkably uniform in temperature? When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it has almost exactly the same temperature in all directions. This uniformity suggests that different regions of the early universe were once in contact with each other, able to exchange energy and reach thermal equilibrium. But according to standard Big Bang cosmology, regions on opposite sides of the observable universe should never have been in causal contact. Light from one region wouldn't have had enough time to reach the other. It's like finding that two people who have never met and live on opposite sides of the world are wearing identical, unique outfits. Possible, but so unlikely that it demands an explanation. Guth's solution was elegant and radical: cosmic inflation. He proposed that in the first tiny fraction of a second after the Big Bang, we're talking about a period so brief it makes a nanosecond look like an eternity, the universe underwent a phase of exponential expansion. During this inflationary epoch, the universe grew by a factor of at least 10 to the power of 26, transforming a region smaller than a proton into something the size of a grapefruit in less time than it takes light to cross the nucleus of an atom. This rapid expansion would explain the uniformity problem. Regions that appear disconnected today were once in close contact before inflation stretched them apart. But inflation also suggests something profound about the nature of time itself, because if inflation can happen once, creating our observable universe from a tiny patch of space, why can't it happen again and again? And in fact, why wouldn't it be happening right now, in regions beyond our cosmic horizon? This leads us to one of the most mind-expanding concepts in modern cosmology: eternal inflation. Picture, if you will, a vast ocean of space undergoing continuous inflation. Occasionally, regions of this inflating space undergo phase transitions, creating bubble universes like ours where inflation stops and matter and radiation can form. Each bubble becomes its own cosmos, with its own Big Bang, its own galaxies, its own potential for life. But here's the kicker: the background process of inflation never stops. It's eternal, constantly creating new bubble universes in an infinite multiverse. And if this picture is correct, then our universe, with its 13.8 billion year age, is just one temporary island of stability in an ocean of space that has been inflating forever. Forever. That word should make you pause, because if eternal inflation is real, then the process that gave birth to our universe has no beginning. It extends infinitely into the past, creating an endless sequence of bubble universes, each with their own local beginning, but embedded in a larger process that transcends time as we understand it. This is where we encounter our first glimpse of a universe that might indeed be older than time itself. Not older than time in our universe, but older than the concept of time that applies to any particular universe. The inflating background space-time exists in a kind of eternal present, constantly creating new temporal domains, but itself transcending the temporal boundaries that limit each individual cosmos. But let's dig deeper into this rabbit hole, because the story gets even stranger. In the 1980s, physicist James Hartley and Stephen Hawking proposed a radical solution to the problem of the universe's beginning. Instead of trying to understand what happened before the Big Bang, they suggested that perhaps the question itself was based on a false premise. Their idea, known as the Hartle-Hawking no-boundary proposal, uses the mathematical machinery of quantum mechanics to describe the origin of the universe. In quantum mechanics, particles don't have definite positions and velocities until they're measured. Instead, they exist in a state of superposition, embodying all possible states simultaneously until observation collapses this uncertainty into a specific outcome. Hartley and Hawking suggested that the universe itself might have originated from a similar quantum state. In their model, as you approach the Big Bang, time itself becomes quantum mechanical. The sharp distinction between time and space that we take for granted in our everyday experience begins to blur. Time, in a sense, becomes imaginary, not in the sense of being fictional, but in the mathematical sense of involving imaginary numbers. In this quantum realm, the universe doesn't have a definite beginning in time, because time itself doesn't have a definite meaning. Instead, the universe emerges from a quantum foam of possibilities, where the very concepts of before and after dissolve into quantum uncertainty, The universe, in effect, creates itself through a bootstrap process that sidesteps the need for an external cause or a temporal beginning. This might sound like mystical nonsense, but it's grounded in rigorous mathematical physics. The same quantum mechanics that governs the behavior of atoms and particles might also govern the origin of space and time themselves. And if this is true, then asking what came before the Big Bang is like asking what happens when you divide by zero. The question assumes a framework that breaks down at exactly the point you're trying to investigate, but the Hartley-Hawking proposal raises its own mind-bending implications. If the universe bootstraps itself into existence through quantum processes, then in some sense it exists outside the normal flow of causation. It doesn't need a cause because it is its own cause, creating the very temporal framework within which causation operates. This brings us to another profound puzzle that emerges when we study the universe's deepest secrets. In 1998, two independent teams of astronomers made a discovery that shocked the scientific world. They were studying distant supernovae, stellar explosions so bright they can be seen across billions of light years, to measure the expansion rate of the universe. Everyone expected to find that this expansion was gradually slowing down due to the gravitational pull of all the matter in the universe. Instead, they found the opposite. The expansion of the universe is accelerating. Something is pushing space itself apart with ever-increasing vigor, overpowering the attractive force of gravity on cosmic scales. Scientists dub this mysterious influence dark energy, though it might be more honest to call it, we have no idea what this is, energy. Dark energy makes up about 68% of the universe's total energy budget. Think about that for a moment. More than 2/3 of everything that exists is composed of something we don't understand, something that seems to be woven into the very fabric of space itself, and this dark energy appears to be constant. As the universe expands, more space is created, and with it, more dark energy. This creates a troubling picture for the far future. If dark energy continues to drive accelerating expansion, then galaxies will become increasingly isolated from one another. Stars will eventually burn out, black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy, a cold, dark, empty expanse where nothing interesting can ever happen again. But here's where the story takes another unexpected turn. Some cosmologists have suggested that dark energy might not be constant. If it grows stronger over time, it could lead to something called the Big Rip, where the expansion becomes so violent that it tears apart galaxies, stars, atoms, and eventually even space and time themselves. The universe would literally rip itself apart in a crescendo of cosmic destruction. Alternatively, if dark energy weakens or changes sign, it might eventually reverse the expansion, causing the universe to collapse back into a big crunch, a reverse Big Bang that would compress all matter and energy back into a singularity. And here's where things get really interesting. Some models suggest that this big crunch could be followed by another Big Bang, creating a new cycle of cosmic evolution. This leads us to the concept of a cyclic universe, an idea that has ancient philosophical roots but has been given new life by modern physics. In cyclic models, the universe goes through endless phases of expansion and contraction, with each cycle potentially lasting trillions of years. From this perspective, our current universe, with its 13.8 billion year age, is just one breath in an infinite cycle of cosmic respiration. The cyclic universe idea addresses one of the deepest philosophical problems in cosmology. Why does anything exist at all? If the universe had a definite beginning, we're forced to confront the question of what caused that beginning. But if the universe is eternal, cycling through endless phases of birth, evolution, and death, then existence becomes a brute fact that requires no external explanation. But the cyclic model faces its own challenges. Each cycle would increase the universe's entropy, and there's no known mechanism for resetting the cosmic clock to perfect order. It's like trying to unscramble an egg or unmix cream from coffee. Thermodynamics seems to put a hard limit on how many times the universe could cycle before running down completely. Yet some physicists have proposed solutions to this entropy problem. Paul Steinhardt and Neil Turok developed a model based on string theory where the universe cycles between phases separated by cosmic brains, higher dimensional surfaces that occasionally collide, triggering new Big Bangs. In their model, each collision resets the cosmic clock, allowing for genuinely eternal cycling. Other theorists have suggested that entropy might not be the insurmountable barrier it appears to be. In an infinite universe, statistical fluctuations could occasionally create pockets of low entropy, like waves forming spontaneously on a calm ocean. These fluctuations could seed new cycles of cosmic evolution, allowing the universe to refresh itself through sheer chance given enough time. But perhaps the most radical solution comes from loop quantum cosmology, a theory that applies the principles of quantum mechanics to the universe's geometry itself. In this framework, space and time are not continuous, but are made up of discrete quantum units, a kind of cosmic pixelation at the smallest scales. Loop quantum cosmology suggests that the Big Bang wasn't really a bang at all, but a big bounce. As a previous universe collapsed toward a singularity, quantum effects would eventually become strong enough to halt the collapse and reverse it into expansion. The universe would bounce like a cosmic rubber ball, transitioning from contraction to expansion without ever reaching infinite density. This quantum bouncing could be eternal, with the universe cycling through endless phases of expansion and contraction. Each cycle would erase most traces of the previous one, making it nearly impossible for us to detect evidence of cosmic reincarnations that occurred before our current big bounce. From this perspective, our universe isn't 13.8 billion years old. That's just how long it's been since the most recent bounce. The underlying cosmic process might be infinitely old, cycling through an endless sequence of births and deaths that stretch back through eternity. But let's step back and consider what all of these theories are really telling us about the nature of time itself. In our everyday experience, time seems like a river flowing in one direction, carrying us from past through present toward an uncertain future. We remember the past, but not the future. Cause precedes effect. Entropy increases. The arrow of time seems as fundamental as the law of gravity, yet physics tells a different story. Einstein's theory of relativity reveals that time is not universal, but relative, flowing at different rates depending on your speed and the strength of nearby gravitational fields. Time dilates and contracts like a cosmic accordion, stretching and compressing based on your reference frame. Even more fundamentally, the equations of physics are largely time-symmetric. If you were to watch a movie of two billiard balls colliding and bouncing apart, you couldn't tell whether the movie was running forward or backward just by looking at the physics. The fundamental laws don't distinguish between past and future. This raises a profound question. If the laws of physics don't define a preferred direction of time, where does the arrow of time come from? Why do we remember the past, but not the future? Why does entropy increase? Why do causes precede effects? The answer seems to lie in the initial conditions of our universe. The Big Bang created a cosmos in a state of extremely low entropy, a highly ordered configuration where all matter and energy were compressed into a tiny, hot, dense region. As the universe expanded and cooled, this initial order gradually dissolved into increasing disorder, and this process of entropy increase is what creates our subjective experience of the arrow of time. But here's the crucial insight. The arrow of time depends on the universe having a special beginning. If the universe is eternal, cycling through endless phases, then the very foundation of temporality, as we understand it, becomes questionable. In an eternal cosmos, every moment has always existed and will always exist. The distinction between past, present, and future becomes as arbitrary as the distinction between here and there in infinite space. This leads us to one of the most profound questions in modern physics and philosophy. Is time real? It's a question that has puzzled thinkers for millennia. The ancient Greek philosopher Parmenides argued that time was an illusion, that reality consisted of an eternal, unchanging being. Heraclitus disagreed, claiming that change and flux were the fundamental nature of reality. Einstein himself wrestled with this question. He once comforted a friend grieving the death of a mutual acquaintance by writing, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. From the perspective of relativity, all moments in time are equally real. The universe is like a four-dimensional block where past, present, and future all exist simultaneously. This view, known as eternalism, or the block universe theory, suggests that time is more like space than like the flowing river of our experience. Just as we don't think of distant places as being less real than our current location, perhaps we shouldn't think of distant times as being less real than the present moment. If eternalism is correct, then the universe isn't getting older in any fundamental sense. All moments, including the Big Bang, the formation of galaxies, the evolution of life, and the heat-death of the cosmos, exist eternally in the four-dimensional block of space-time. From this timeless perspective, the universe is indeed older than time because it exists outside the temporal flow entirely. But let's explore another fascinating possibility that emerges from quantum mechanics. In the 1950s, physicist Hugh Everett proposed the many worlds interpretation of quantum mechanics. According to this theory, every quantum measurement doesn't just reveal a pre-existing property of a particle, it actually splits the universe into multiple branches, each containing a different outcome. When you flip a coin, for instance, the universe splits into two branches, one where you observe heads and another where you observe tails. Both outcomes are equally real, but you only experience one of them because you happen to find yourself in that particular branch of the multiverse. If many worlds is correct, then every moment splits into countless branches corresponding to all possible quantum outcomes. The universe becomes a vast, ever-branching tree of possibilities, with each branch representing a different history. From this perspective, all possible versions of the universe exist simultaneously in a quantum multiverse. This branching structure raises fascinating questions about the nature of time and existence. In the many worlds multiverse, every possible history is real, including histories where the universe evolved very differently from our own. There might be branches where the fundamental constants of physics are different, where stars never formed, where life never evolved, or where civilizations far more advanced than ours already exist. More relevantly to our question, there might be branches where the universe is much older or much younger than 13.8 billion years. If eternal inflation is combined with many worlds quantum mechanics, we get a picture of reality that is not just spatially infinite, but also infinite in possibility space. Every conceivable variation of cosmic evolution would be realized somewhere in the multiverse. From this perspective, our universe with its particular age and history is just one thread in an infinite tapestry of possibilities. The question of whether the universe is older than time becomes meaningless because all possible ages and all possible relationships between existence and temporality are realized somewhere in the quantum multiverse. But let's consider yet another possibility that pushes the boundaries of our cosmic imagination even further. Some theorists have suggested that consciousness itself might play a fundamental role in the nature of reality and time. This isn't as mystical as it might sound. Consciousness is, after all, the one phenomenon we know exists with absolute certainty because we experience it directly. The relationship between consciousness and time has puzzled philosophers and scientists for centuries. We seem to experience time as a flowing river with a definite present moment that moves from past toward future. Yet physics suggests that this flowing present is an illusion, that all moments are equally real in the block universe of space-time. Some researchers have suggested that consciousness might be what creates the experience of temporal flow. The physicist Roger Penrose and anesthesiologist Stuart Hameroff have proposed that consciousness arises from quantum processes in the brain that somehow tap into the fundamental structure of space-time itself. If consciousness is indeed woven into the fabric of reality at the deepest level, then perhaps the universe has been conscious in some sense for far longer than the 13.8 billion years since the Big Bang. Maybe consciousness is a fundamental feature of existence that transcends individual brains and nervous systems. This might sound like science fiction, but it addresses a real puzzle in our understanding of consciousness. How does subjective experience arise from objective physical processes? How does the feeling of seeing red or experiencing joy emerge from the firing of neurons? This is what philosophers call the hard problem of consciousness, and despite centuries of study, we're no closer to solving it. One intriguing possibility is that consciousness is a fundamental feature of the universe, like mass or electric charge. In this view, called panpsychism, every particle has some rudimentary form of experience, and complex consciousness emerges when these micro-experiences are organized into integrated systems like brains. If panpsychism is correct, then the universe has been conscious in some sense since its earliest moments. The atoms formed in the first stars, the molecules assembled in primordial oceans, the cells that gave rise to life, all would possess some form of inner experience. Consciousness wouldn't be something that evolved late in cosmic history, but would be as old as matter and energy themselves. This raises the profound possibility that our question, whether the universe is older than time, might not just be a scientific inquiry, but a kind of cosmic self-reflection. If consciousness is fundamental, then perhaps the universe is literally questioning its own nature through our minds. We are the cosmos becoming aware of itself, probing its own deepest mysteries through the tools of science and philosophy. But let's return to more concrete scientific territory and consider some recent developments that shed new light on the universe's age and the nature of time. In recent decades, astronomers have developed increasingly sophisticated methods for measuring cosmic distances and ages. By studying the light from distant galaxies, they can reconstruct the history of cosmic expansion and determine when different events occurred. One of the most precise tools for this cosmic archaeology is the study of Type 1a supernovae. These stellar explosions have a characteristic brightness that allows astronomers to use them as standard candles for measuring distances to faraway galaxies. By comparing how bright these supernovae appear with how bright they should be at their measured distances, astronomers can map the expansion history of the universe with remarkable precision. Another crucial tool is the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. This radiation carries with it a detailed snapshot of the universe when it was only 380,000 years old, just after it had cooled enough for the first atoms to form. By analyzing tiny temperature fluctuations in this cosmic background glow, scientists can determine the fundamental parameters of our universe with extraordinary accuracy. These measurements have converged on a remarkably consistent picture. The universe is 13.799 billion years old, plus or minus about 21 million years. That's a precision of better than 0.2%. Imagine measuring the width of the United States and being accurate to within a few city blocks. But here's something interesting. Some of the oldest stars in our galaxy appear to be nearly as old as the universe itself. Globular clusters, dense collections of ancient stars, contain stars that formed when the universe was less than 1 billion years old. These stellar fossils carry in their light the chemical signatures of a cosmos that was very different from today's universe. The precision of these age measurements raises intriguing questions. If we can measure the universe's age so precisely, what does this tell us about the nature of time itself? The fact that we can assign a definite age to the cosmos suggests that time, at least within our observable universe, behaves like a well-defined physical quantity. Yet this precision also highlights the mystery of what lies beyond our observational horizons. The observable universe, the region from which light has had time to reach us, is finite, bounded by the cosmic horizon. But the true universe might extend far beyond what we can see, possibly infinitely far. If inflation is correct, then our observable universe is just a tiny bubble in a vast inflating space-time. The entire process of eternal inflation might extend infinitely into space and infinitely into the past, making our precisely measured age of 13.8 billion years just a local property of our particular cosmic neighborhood. This brings us to one of the deepest puzzles in modern cosmology, the fine-tuning problem. The fundamental constants of physics, the strength of gravity, the mass of the electron, the speed of light, all have values that seem precisely adjusted to allow for the existence of stars, planets, and life. Change any of these constants by even a small amount, and the universe would be a very different and probably much more boring place. For instance, if gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars might never form at all. If the strong nuclear force were a bit different, atomic nuclei might not be stable, and complex chemistry would be impossible. The universe seems to be walking a cosmic tightrope, balanced on a knife's edge between chaos and emptiness. This apparent fine-tuning has led some scientists to suggest that we live in a multiverse where all possible combinations of physical constants are realized. In such a multiverse, universes like ours, with constants perfectly tuned for complexity and life, would be rare but inevitable. We find ourselves in a life-friendly universe, not because it was designed that way, but because we couldn't exist in any other kind. But the multiverse solution to fine-tuning raises its own profound questions about the nature of time and existence. If there are infinitely many universes with infinitely many different histories, then every possible moment exists somewhere in the multiverse. Past, present, and future become relative concepts, meaningful only within the context of a particular universe or a particular conscious observer. In such a multiverse, our question about whether the universe is older than time takes on new meaning. There would be universes where time flows backward, universes where time branches and merges like a river delta, universes where time has multiple dimensions, and universes where time doesn't exist at all. The multiverse would contain every possible relationship between existence and temporality. This leads us to consider another fascinating possibility, digital physics, or the idea that reality might be computational in nature. Some physicists and philosophers have suggested that the universe might be running on something like a cosmic computer, with the laws of physics acting as the program and particles and fields as the data being processed. If reality is indeed computational, then time might be nothing more than the execution of a cosmic algorithm. Each moment would correspond to a step in the computation, and the flow of time would be the sequential processing of information. From this perspective, the universe wouldn't be older than time, because time would simply be the measure of computational progress. The digital physics hypothesis gains some support from quantum mechanics, which seems to suggest that information, rather than matter or energy, might be the fundamental constituent of reality. Quantum bits, qubits, can exist in superposition states that allow them to process vastly more information than classical bits. If the universe is quantum computational in nature, it might be processing unimaginable amounts of information every moment. This computational view of reality also connects to recent developments in artificial intelligence and machine learning. As we create increasingly sophisticated AI systems, we're beginning to understand how complex behaviors and apparent intelligence can emerge from simple computational rules. Perhaps consciousness itself is a kind of computation, and perhaps the universe's apparent intelligence, its ability to evolve complexity, life, and awareness, reflects its fundamentally computational nature. If the universe is indeed a cosmic computer, then our question about its age becomes a question about how long the program has been running. But in a truly sophisticated computational system, especially one involving quantum processing, the concept of runtime becomes ambiguous. Quantum computers can in some sense explore all possible computational paths simultaneously, existing in superposition states that transcend our normal understanding of sequential time. From this quantum computational perspective, the universe might not have a single definite age, but might exist in a superposition of all possible ages simultaneously. Our measurement of 13.8 billion years would be the result of quantum decoherence, the process by which quantum superposition states collapse into definite classical outcomes when observed. But let's step back from these speculative possibilities and consider what we can actually observe about the universe's relationship to time. One of the most remarkable discoveries of the past few decades is that space itself has a kind of memory. Gravitational waves, ripples in the fabric of space-time, carry information about the cosmic events that created them. When two black holes spiral into each other and merge, they create gravitational waves that propagate outward at the speed of light, carrying with them the signature of that cosmic collision. These waves can travel for billions of years across the universe before finally reaching Earth, where sophisticated detectors like LIGO can measure distortions in space-time that are smaller than 1,000th the width of a proton. The detection of gravitational waves has opened up an entirely new way of studying the universe. Unlike light, which can be absorbed or scattered by intervening matter, gravitational waves pass through everything nearly unaffected. They provide us with a direct view of space-time dynamics, allowing us to observe the universe in ways that were impossible just a few decades ago. More remarkably, gravitational waves carry information about events that occurred when the universe was very young. The cosmic microwave background provides a snapshot of the universe when it was 380,000 years old, but gravitational waves could potentially give us information about events that occurred when the universe was just a fraction of a second old. If the universe underwent inflation in its earliest moments, this rapid expansion would have created primordial gravitational waves that should still be propagating through space today. Detecting these waves would provide direct evidence for inflation and give us unprecedented insight into the universe's first moments. The memory of space-time extends even further back. Some theories suggest that quantum fluctuations in the fabric of space and time during the Planck epoch, the first 10 to the power of -43 seconds after the Big Bang, might have left permanent imprints on the structure of space-time itself. These quantum scars could carry information about the universe's birth that predates even the formation of matter and energy. If such quantum archaeological records exist, they would represent a kind of cosmic DNA, information about the universe's origins encoded in the very geometry of space and time. Reading this information would be like deciphering the universe's birth certificate, potentially revealing whether our cosmos is truly 13.8 billion years old or whether it's connected to an even more ancient cosmic process. This brings us to one of the most profound questions we can ask. What is the universe expanding into? When we say space itself is expanding, we usually mean that distances between galaxies are increasing. But this raises the puzzling question of what lies beyond the expanding boundary of space. The standard answer is that this question doesn't make sense. Space isn't expanding into anything because there is no outside for it to expand into. Space and time together constitute the entire arena of existence, and asking what lies beyond them is like asking what's north of the North Pole. but some theories suggest that our space might indeed be embedded in a higher dimensional realm. String theory, for instance, proposes that the three dimensions of space we experience are just part of a higher dimensional bulk space that contains multiple universes. From this perspective, our expanding universe might be like a soap bubble growing in a multidimensional foam. If our universe is embedded in a higher dimensional space, then the process that created our Big Bang might be just one event in a much larger cosmic story. The higher dimensional realm might be eternal, hosting countless Big Bangs and cosmic evolutions across vast expanses of hyperspace and hypertime. This possibility connects to some of the most advanced theories in modern physics. M-theory, an extension of string theory, suggests that fundamental particles might not be point-like objects, but rather tiny vibrating strings or higher dimensional membranes. These objects exist and vibrate in multiple dimensions beyond the three spatial dimensions we observe. In some versions of M-theory, our entire universe is a three-dimensional membrane floating in a higher dimensional bulk space. Other universes would be other branes, potentially vibrating at different frequencies or separated from us by extra dimensions that we can't directly perceive. Occasionally, these branes might collide, and such collisions could trigger Big Bangs and the birth of new universes. From this perspective, our Big Bang wasn't the beginning of everything, but rather the result of a collision between higher dimensional objects in an eternal multiverse. If this brain world scenario is correct, then our universe with its 13.8 billion year history is just one episode in an eternal cosmic drama playing out in higher dimensions. The question of whether the universe is older than time becomes a question about whether the higher dimensional bulk space has its own temporal structure that transcends the time experienced within individual brains. But perhaps the most profound implication of all these theories is what they tell us about our place in the cosmic story. For most of human history, we thought we lived at the center of the universe. Then we discovered that Earth orbits the Sun, that the Sun is just one star among billions in our galaxy, and that our galaxy is just one among billions in the observable universe. Now we're confronting the possibility that our observable universe might be just one bubble in an infinite multiverse, that our 13.8 billion year history might be just one moment in an eternal cosmic process, and that our very concepts of space and time might be provincial features of our local cosmic neighborhood rather than universal principles. This cosmic humility is both daunting and liberating. Daunting because it suggests that everything we know and care about might be infinitesimally small in the grand scheme of existence. Liberating because it opens up vistas of possibility that dwarf our wildest imagination. Consider what this means for the future of human knowledge and exploration. If the multiverse is real, then there might be universes where the laws of physics are different, where impossible things become possible, where consciousness takes forms we can't even imagine. The boundaries of what can exist and what can be known might be far more flexible than we assume. Even more intriguingly, some theories suggest that sufficiently advanced civilizations might be able to influence or even create universes. If consciousness can affect quantum systems, as some interpretations of quantum mechanics suggest, then perhaps sufficiently organized consciousness could affect the structure of space-time itself. This possibility connects to ancient philosophical and religious ideas about the relationship between mind and cosmos. Many traditions have suggested that consciousness is not merely a product of the universe, but plays a fundamental role in its existence. Modern physics, with its emphasis on the role of observation in quantum mechanics, gives these old ideas new relevance. If consciousness can influence physical reality, then the question of whether the universe is older than time becomes entangled with questions about the nature and origin of consciousness itself. Perhaps the universe exists in a state of eternal becoming, constantly creating itself through the interplay between physical processes and conscious observation. This brings us full circle to where we started, standing in your backyard, looking up at the stars, wondering about the nature of time and existence. But now, after our journey through modern cosmology and quantum physics, that simple act of stargazing has taken on new depths of meaning. Each photon entering your eye has traveled across vast distances and times to reach you. Some of that light left distant stars when the universe was much younger, carrying with it information about cosmic epochs that existed long before Earth formed. You are literally seeing the past, observing events that happened millions or billions of years ago. But if some of the theories we've explored are correct, you might also be seeing evidence of processes that transcend the 13.8 billion year history of our observable universe. The cosmic microwave background radiation that bathes you every moment might carry within it traces of eternal inflation, quantum fluctuations that originated in a timeless realm beyond our cosmic horizon. The very atoms in your body were forged in the nuclear furnaces of ancient stars, making you a living embodiment of cosmic history. The carbon in your muscles, the oxygen in your lungs, the iron in your blood, all of these elements were created billions of years ago in stellar explosions that scattered the building blocks of life across the galaxy. But if the universe is truly older than time in the ways we've explored, then those ancient stellar processes might themselves be echoes of even more fundamental cosmic cycles. The matter and energy that compose your body might have participated in countless previous cosmic incarnations, cycling through endless phases of stellar birth and death in universes that preceded our own. This perspective transforms the simple act of existing into something almost mystical. You are not just a temporary arrangement of atoms that happen to achieve consciousness. You are a focal point where the universe becomes aware of itself, a place where cosmic history crystallizes into subjective experience. Through your eyes, the universe observes its own evolution. Through your mind, it contemplates its own mysteries. And what mysteries they are. As we've seen, every answer in cosmology seems to lead to deeper questions. We've discovered that the universe is expanding, but we don't understand dark energy. We've measured the cosmic microwave background with extraordinary precision, but we can't explain why the universe began in such a special state. We've detected gravitational waves from black hole mergers, but we don't know what happens to information that falls into black holes. Each breakthrough in our understanding reveals new depths of cosmic mystery. It's as if the universe is designed to always stay one step ahead of our comprehension, revealing just enough of its secrets to keep us searching for more. This might not be a coincidence. If consciousness plays a fundamental role in the structure of reality, then perhaps the universe maintains its mystery precisely to keep conscious beings engaged in the quest for understanding. Consider how this relates to our central question about the universe's age. The fact that we can ask whether the universe is older than time suggests that our minds are capable of conceiving possibilities that transcend our immediate experience. We can imagine eternal inflation, quantum creation, ex nihilo, cyclic cosmologies, and multidimensional brains precisely because consciousness seems to have a reach that extends beyond the boundaries of any particular physical system. This cognitive transcendence might itself be a clue about the nature of reality. If our minds can conceive of eternal processes, timeless existence, and infinite multiverses, perhaps it's because these concepts reflect genuine features of the cosmic order. Our ability to ask questions that push beyond the apparent boundaries of space and time might indicate that we are connected to aspects of reality that truly do transcend those boundaries. But let's explore another fascinating aspect of our cosmic situation, the horizon problem. We can only observe the universe out to a certain distance, about 46.5 billion light-years in any direction. This cosmic horizon marks the boundary beyond which light hasn't had enough time to reach us since the Big Bang. Everything beyond this horizon is causally disconnected from us, at least for now. Yet the universe almost certainly extends far beyond this observational boundary. If space is infinite, then our observable universe is just a finite bubble in an infinite ocean of space. If eternal inflation is correct, then new regions of space are constantly being created beyond our horizon, regions that we will never be able to observe, no matter how long we wait. This situation raises profound questions about the nature of existence and reality. Do regions of the universe that we can never observe still exist in a meaningful sense? If a galaxy forms and evolves beyond our cosmic horizon, with no possibility of ever interacting with us or sending us information, in what sense can we say it exists? These questions echo ancient philosophical puzzles about unobserved reality. If a tree falls in a forest with no one around to hear it, does it make a sound? But the cosmic version is far more dramatic. If entire universes exist beyond our observational horizon, with their own big bangs, their own galaxies, their own potential for life and consciousness, do they exist in the same sense that our observable universe exists? The question becomes even more puzzling when we consider quantum mechanics. Some interpretations suggest that quantum systems don't have definite properties until they're observed. If this is true, then what happens to regions of the universe that can never be observed by any conscious being? Do they remain in eternal quantum limbo, never quite achieving the definiteness that observation seems to confer? Or perhaps the act of observation is more fundamental than we realize? Maybe consciousness doesn't just reveal pre-existing properties of quantum systems, but actually participates in their creation. If this is the case, then the boundaries of the observable universe might not just mark the limits of our knowledge, but might actually define the boundaries of definite existence itself. This possibility connects to some of the most speculative ideas in modern physics. The physicist John Wheeler suggested that the universe might be participatory in nature, with consciousness playing an active role in determining physical reality. In his famous phrase, "The universe exists in a state of it from bit," physical reality emerging from information and observation rather than the other way around. If Wheeler's vision is correct, then our question about whether the universe is older than time becomes a question about the relationship between consciousness and temporal existence. Perhaps time itself emerges from the interaction between physical processes and conscious observation. The universe might exist in a timeless quantum state until conscious beings emerge to observe it, at which point the flow of time crystallizes into definite form. This would mean that the universe's apparent age of 13.8 billion years might be a kind of retroactive creation, established by the fact that conscious observers eventually emerged to measure it. The past might not be fixed and determinate, but might continue to be shaped by present and future observations. Such ideas push the boundaries of scientific speculation, but they're grounded in genuine puzzles about the nature of quantum mechanics and consciousness. The fact that observation seems to play a special role in quantum theory suggests that the relationship between mind and reality might be more intimate than classical physics assumed. But let's return to more observationally grounded territory and consider what recent discoveries are telling us about the universe's deep history. One of the most exciting developments in modern astronomy is the James Webb Space Telescope, which can peer further back in cosmic time than any previous instrument. By observing in infrared wavelengths, Webb can see through the cosmic dust that obscures our view of the early universe. It's giving us unprecedented glimpses of the first galaxies that formed when the universe was less than 1 billion years old. These ancient galaxies appear surprisingly mature and massive, suggesting that galaxy formation might have proceeded more rapidly in the early universe than we previously thought. Some of these early galaxies are so large and well-developed that they challenge our models of cosmic evolution. It's as if we expected to find cosmic toddlers, but instead discovered cosmic teenagers, galaxies that seem too sophisticated for their apparent age. This doesn't necessarily mean our measurement of the universe's age is wrong, but it might mean that the early universe was more dynamic and complex than we realized. These observations also reveal something profound about the nature of cosmic time. When we look at these distant galaxies, we're seeing them as they were billions of years ago, but we're seeing them now, in our present moment. The light that left those galaxies when the universe was young is just now reaching our telescopes, creating a strange temporal paradox where past and present collapse into a single moment of observation. This temporal collapse is more than just a curious feature of astronomy. It reflects something deep about the structure of space-time itself. Einstein showed us that simultaneity is relative, that there's no universal now that applies throughout the cosmos. Events that appear simultaneous to one observer might appear sequential to another, depending on their relative motion and position in gravitational fields. From this relativistic perspective, the question of whether the universe is older than time becomes even more complex. Time itself is not absolute, but is woven into the fabric of space-time in ways that depend on your reference frame. An observer traveling at high speed relative to us would measure different ages for cosmic events. An observer in a strong gravitational field would see time flowing differently than we do. If time is relative in this way, then perhaps the universe's relationship to time is also relative. From some perspectives, the universe might appear to have a definite age. From others, it might appear eternal. From still others, the very concept of age might become meaningless. This relativistic view of time connects to some of the deepest questions in physics and philosophy. What is the relationship between subjective time, the time we experience in consciousness, and objective time as measured by clocks and physics? Are they the same thing, or are they fundamentally different phenomena that happen to correlate in our everyday experience? Some researchers have suggested that consciousness might experience time in a fundamentally different way than physical systems measure it. While physical time might be relative and observer-dependent, conscious time might have its own structure that transcends the physics of space-time. If this is true, then perhaps consciousness provides a kind of universal reference frame for temporal experience. No matter how fast you travel or how strong the gravitational fields around you, your subjective experience of temporal flow might remain constant. Consciousness might exist in its own temporal domain that interfaces with, but is not entirely determined by physical space-time. This possibility raises fascinating questions about the nature of personal identity and continuity. If consciousness experiences time differently than physics measures it, then what does it mean for you to persist through time? Are you the same person who went to sleep last night and woke up this morning? Or are you a new conscious entity with inherited memories? These questions become even more complex when we consider the possibility of digital consciousness or mind uploading. If consciousness can be divorced from biological brains and instantiated in digital form, then the relationship between conscious time and physical time becomes even more flexible. Digital consciousness might experience time at whatever rate its computational substrate allows, potentially speeding up or slowing down temporal experience at will. From the perspective of an accelerated digital consciousness, the 13.8 billion-year history of the universe might be experienced in mere moments. Conversely, a single human lifetime might be stretched out across subjective eons. The relationship between cosmic time and conscious time would become completely malleable. But perhaps the most profound implication of all these considerations is what they tell us about the nature of existence itself. Throughout our exploration, we've encountered multiple ways in which the universe might transcend our conventional understanding of time: eternal inflation, quantum creation, cyclic cosmologies, higher dimensional embedding, and conscious participation in reality. Each of these possibilities suggests that existence might be far more fundamental and enduring than we typically assume. If any of them are correct, then the universe's existence doesn't depend on time in the way we might naively expect. Instead, time emerges from, or is embedded within, a more fundamental level of reality that transcends temporal boundaries. This view has profound implications for how we understand our own existence and mortality. If the universe is truly older than time, then perhaps consciousness participates in this transcendence of temporal limitations. Perhaps the awareness that allows us to contemplate these cosmic mysteries is itself connected to the timeless aspect of reality. This doesn't necessarily mean that individual consciousness survives physical death. That's a separate question with its own complexities. But it might mean that consciousness as a cosmic phenomenon is as fundamental and enduring as matter and energy. If consciousness is woven into the fabric of reality at the deepest level, then it participates in whatever makes the universe older than time. As we near the end of our cosmic journey, it's worth reflecting on what this exploration has revealed about the limits of human knowledge and understanding. We've pushed our concepts to their breaking points, exploring possibilities that challenge our most basic assumptions about time, space, causation, and existence. Yet for all our theoretical sophistication, we must remain humble about what we actually know. The universe continues to surprise us with every new observation and discovery. Dark matter and dark energy, which together make up 95% of the universe, remain profound mysteries. The nature of consciousness, despite being our most intimate experience, continues to elude scientific explanation. Perhaps this ignorance is not a temporary limitation to be overcome, but a permanent feature of our cosmic situation. Perhaps the universe is structured in such a way that finite conscious beings can never achieve complete understanding of their cosmic context. There might always be deeper layers of mystery, more fundamental questions, greater puzzles to explore. If this is true, then our question about whether the universe is older than time might not have a final, definitive answer. Instead, it might be a kind of koan, a puzzle designed not to be solved, but to stretch our minds and deepen our appreciation for the mystery of existence. This perspective transforms the scientific quest from a march toward final understanding into an ongoing conversation with cosmic mystery. Each discovery doesn't just answer old questions, but reveals new depths of puzzlement. Each breakthrough in understanding opens up new vistas of the unknown. From this viewpoint, science becomes a form of cosmic art, a way of creating ever more beautiful and profound questions about the nature of reality. The elegant mathematics of general relativity, the strange predictions of quantum mechanics, the vast scales revealed by cosmology, all of these become not just tools for prediction and control, but ways of participating in the universe's ongoing self-exploration. And perhaps that's the deepest answer to our question about whether the universe is older than time. The universe might not just be older than time. It might be the very process by which time, space, matter, energy, and consciousness emerge from a more fundamental creative principle that transcends all categories. If this is true, then every moment of our existence participates in this cosmic creativity. Every thought, every observation, every question contributes to the universe's ongoing process of self-discovery. When you look up at the night sky and wonder about the nature of time and existence, you're not just a passive observer of cosmic history. You're an active participant in the universe's attempt to understand itself. This participation gives profound meaning to the human quest for knowledge and understanding. We're not just accidentally conscious beings on a small planet orbiting an ordinary star. We're focal points of cosmic self-awareness, places where the universe achieves sufficient complexity to reflect on its own nature. Our questions about time, infinity, and existence might themselves be evolution of cosmic consciousness. Through our scientific instruments and mathematical theories, the universe develops new ways of observing and understanding itself. Through our philosophical reflections and existential questions, it explores the meaning and purpose of its own existence. From this perspective, the age of the universe, whether 13.8 billion years or infinite or somehow beyond temporal measurement entirely, becomes less important than the ongoing process of cosmic becoming that we witness and participate in every moment. We are the universe in the process of figuring itself out, and that process might be more fundamental than any particular answer we discover. So as you stand in your backyard tonight, looking up at the stars, remember that you're not just observing the universe from outside, you're the universe observing itself from within. The mystery of whether the cosmos is older than time is not just an abstract puzzle, but a reflection of your own mysterious existence as a conscious being embedded in the cosmic story. And perhaps that's the most beautiful answer of all. The universe might be older than time, precisely because it includes conscious beings like you who can ask such questions. Consciousness might be the universe's way of transcending its own temporal boundaries, of achieving a perspective that encompasses past, present, and future in a single moment of awareness. In that moment of cosmic consciousness, you touch something that might indeed be older than time itself, the creative principle that brings worlds into being, that evolves matter into mind, that transforms cosmic dust into beings capable of contemplating their own existence. Whether we call it consciousness, creativity, love, or simply the mysterious fact that anything exists at all, it might be the most fundamental feature of reality, and so our journey ends where it began, with wonder. But now it's a deeper wonder, informed by all the strange and beautiful possibilities we've explored. The universe might be 13.8 billion years old, or it might be eternal, or it might exist in a state that transcends temporal measurement entirely. What matters is not which answer is correct, but that we live in a reality mysterious enough to make such questions possible. Tonight, when you look up at the stars, you'll see them with new eyes. Each point of light carries with it the possibility of infinite depths, endless time, and cosmic consciousness that might be as old as existence itself. You are part of that story, woven into the very fabric of cosmic becoming. And in your questioning, in your wonder, in your very existence, the universe continues its eternal exploration of what it means to be.